Hello, this lecture will cover pages 138 through 141 of my lecture notes. Please print those pages out and have them in front of you as I present this lecture on integrated circuit specifications, Part B, digital currents and FanOut. In the last lecture we discussed T sub A, operating free air temperature, and the voltage levels, input and output. And we said you read them from right to left: high level input voltage, low level input voltage, high level output voltage, and low level output voltage. In this lecture we're going to talk about the four currents: the high level input current, the low level input current, the high level output current, and the low level output current. The propagation times we've already discussed. You read those from left to right, and there's no real reason why or why not, but they had the convention right to left up here and left to right down here. Could never explain that, but propagation time low to high, propagation time high to low. These are read from left to right, but when you talk about voltages and currents, it's from right to left. Okay, the currents on page number 138. The first two currents we're going to discuss are the high level input current and the low level input current. These are input currents. Whenever you see the I, you have to think of input. You have to think of the input of the device. This is the multiple emitter input. And when you look at a diagram like this, you should be looking at this right here. When you talk about these currents, whether the currents are flowing in or the currents are flowing out, they're talking about this multiple emitter input. Let's take this one emitter here. Is this input here? So this current coming out, is this current coming out up here? And the current flowing into the IC, is that current flowing in? For TTL specifications, if you take a look in the specs, and you should do this, I want you to get out page number 273 for the quad 2 input NAND gate spec. IH max is 40 microamps. It's a reverse leakage current. It's just a very small current that's going to leak back into the device when the output is high, and it's specified as a max. IH max is 40 microamps. So the current here flows back into the device. This current here that's flowing back into the device, when that is a high state, is 40 microamps. IIL max, the low level input current, is minus 1.6 milliamps. It's quite a bit larger. That current flowing from the device, when this state is low, the current coming out, when this state is low, the current coming out of that device is significantly larger. It's 1.6 milliamps. Now, this minus sign here, the nomenclature is, the sign notation is minus currents are currents that are leaving an integrated circuit. Most of the time, we're just going to handle the absolute value here. The direction, this is just a way to symbolize that the current is leaving the integrated circuit. When you see minus currents, that's the only time we're going to use that as a signification that the current's leaving the integrated circuit. And if you look down here, I'm going to talk about IOH and IOL. We're talking about output now. We're looking at the totem pole output. High level output current and low level output current. When you see these currents and I show you a high level output current, when this state is high and that current is coming down this way, it's called a sourcing current. That's this current here. When you see a totem pole output and I talk about a sourcing current, you should see this. This totem pole output is the output of this gate. So this sourcing current coming out is the current coming down here. It's the current coming out of the chip. Okay? And I want you to notice that it's a minus 400 microamps. Low level output is 16 milliamps. Low level output current, this current that's coming down and being sunk to ground. When you think of IOL, you think of this current right here, the sinking current. When this is low, how is this low? This is low because this transistor is saturated, pulling this line low, and that current's going to flow down this way. It's a sink current. It's a current coming down here. Now we're going to put all this together. We're going to take this maximum value of high-level input current and this maximum value of low-level input current and this maximum value of high-level output current and this maximum value of low-level output current, and we're going to put that all together to determine what we call a fan-out. But before we do that, when you discuss these currents down here, we can say for the low-level state here, okay, for the low-level state, that this device sinks 16 milliamps because that's out of the specification. And we can say for the high-level state that in the high state, this particular device will source 400 microamps. Again, it's minus because the current's leaving. That's the only significance of that minus sign. So in the high state, it'll source 400 microamps. In the low state, it'll sink 16 milliamps. Make sure you can get this information out of the specification on page number 273. I want you to see if you can determine where that comes from. High-level input current, the low-level input current, the high-level output current, and the low-level output current. Make sure you can justify all four of these from the specification for TTL. Next, we're going to look at page 139. Page 139, I have a little bit of an exercise for you here. Students usually think that when you drive a motor, or you drive a lamp, or you drive an LED, that you have to drive it with a positive voltage. You have to put a positive voltage out there to turn something on. But I'm going to show you can put a negative voltage out there. You can put a ground voltage out there. You can put 0 volts out, and 0 volts will drive something. Well, how will that work? Well, if we have a small DC motor, this is on page 139. If we have a small DC motor that has a running current specification of 10 milliamps, so in other words, it needs 10 milliamps for this small motor to run, and you can buy many of these. Go to Radio Shack, go online, little DC motor. Which circuit design will run the motor? Which circuit design down here will allow you to run that motor? Well, first of all, one engineer designs it this way. He has an AND gate here. And this AND gate, you have to enable the circuit, so there has to be a 1 here and a 1 here, and you turn on the motor. So, turn on motor, high active signature, enable is a high active signature. So when this is a 1 and this is a 1, this output will be a 1, and the motor should turn on, high active signature. Well, this side of the motor we have tied to ground, and we throw 5 volts out here. If it's a 5 volt, 10 milliamp motor, that should turn on. But how much current are you going to get out of that device? Well, you have to look at the specification. The engineer looks at the specification for IOH max. What's the maximum high-level output current you're going to get? And don't forget, it's a sourcing current. It's coming from VCC down this way and coming out. Well, if you look at the previous page, on page 138, you'll see that IOH max is 400 microamps. 400 microamps is all you're going to get out of this device. You're not getting anywhere near 10 milliamps. So this looks like common sense. Put off 5 volts out here and you turn the motor on, but you can't source the current. So another engineer designs down here, design B. He or she suggests, well, let's use an AND gate here, and let's drive a low active signature here. In other words, a 1 here and a 1 here. We'll put a low out there. So it's a ground. You're throwing out ground, ideally, 0 volts. Well, what happens is on the other side of the motor, you don't tie it to ground like you did. You tie it to VCC. Think about that. You're just going to impress a voltage across here. When this is high here and this is a high all the time, you don't have any voltage across the motor. But what happens when this is a 1 and this is a 1 and the motor said turn on, low active, it goes 0. That bottom transistor turns on and you have current coming this way. Conventional current flows this direction and it is sunk. It's sinking current. And if you look at the previous page, what's IOL max? What's the low-level output current maximum? It's 16 milliamps. Up here, you're only going to get out 400 microamps, never going to work. Down here, when you turn this on with a low active signature, you get current going in this direction. That's going to turn on that motor, and you can sink 16 milliamps. And 16 milliamps is more than enough because you only need 10 milliamps. So design A is not going to work. Design B is the way they do it. Now you know why they use low assertion levels. In most cases with TTL, with most of the gates, you're going to be able to sink current a lot more than you can source. So they always drive things with the low active state, and that's the reason. And then finally, on page 140, let's put I, IH, IIL, IOH, and IOL together. Well, all the voltages went together and they formed noise margins. Well, you don't form noise margins with currents. You form fan-out. What's fan-out? Fan-out is the number of loads within a given logic family that can be driven from one output of a logic gate. Remember I told you this before, that you cannot do this. You can't take an output of a gate here. And let's take it to another inverter. And let's take it down here to one of the inputs of an OR gate. And let's take it down here to an exclusive OR gate. I mean, you're driving 1, 2, 3 different inputs with this one output here. You can't go on indefinitely there. It's called fan out. How many places can you take this before you get into trouble? Well, again, it's real easy to understand this. Here's a NOR gate that's driving one input of an AND gate on page 140. Notice in the low state, when you want a low out here, you're sinking current over here. That's how this line gets low. It gets low because the output totem pole, the lower transistor is saturated, and you're pulling it to ground. So current's flowing from this device to this device, and let's trace it up here. It's coming out here and it's going in here. What it's really doing in the integrated circuit, it's coming down here, out the multiple emitter, and it's coming over the output line, and it's going down to ground. Well, in the low state, how many of these can you tolerate? Here's 1, here's 2, here's 3 or 4 or 5. How many of those can you tolerate before you fill up, before you exceed the 16 milliamps? If you take a look, IIL max was, forget about the minus. Minus just means it's leaving the integrated circuit here. It's 1.6 milliamps. For every one of these you connect up, you have 1.6 milliamps that's flowing back this way. Well, you can tolerate 16 milliamps sinking current over here. So you can very easily determine the low-level fan-out by putting IOL max in the numerator and IIL max, how many of these they are, in the denominator that will fit into here. I want you to calculate the low-level fan-out for TTL by looking at the specification on page 273. And I want to see if you can calculate that using this formula. And the answer should be low-level fan-out is 10. It's not 10 milliamps. It's not 10. No units, because the units, the amps cancel. That's just 10. You can take the output of TTL gates to 10 places and no more. And then I have some people that say, you know what, I took it 11 places. I took it 12 places. I took it 13 places and it worked. Well, yeah, maybe it did, but there's a trade-off there. The manufacturer says, according to this equation, and this equation's good for every logic family, just the specs, the numbers change here. They're saying they'll guarantee a fan out of 10. It may work 11, it may work 12. But the problem is if you tie another output another input on, and another input, you have more current coming back this way. If you go to 11 or 12, you have more current. And for every bit of current you push down through this output, this transistor really looks like a resistance here. You're building up this voltage. In the low state, this voltage, they're no longer going to guarantee 0.4 volts. It'll go to 0.5 volts. It'll go to 0.6 volts. You're cutting into your noise margin. So you might be able to drive 15 different circuits, but your noise margin suffers because VOL max is not 0.4 anymore. It'll go to 0.45 and 0.5 and 0.6, and you're cutting into your noise margin. And when you throw enough currents down through there and it builds this voltage up to 0.8, you don't have any noise margin at all. And then finally on page 141, I want to look at the high-level fan-out in the high state. In the high state, how many devices can you connect up? Because currents for every you only have so much source current here. That source current there, if you remember, that high-level output current max was 400 microamps. You're only going to get 400 microamps. So how many places can you drive? Well, if you take a look, high-level output max was 0.4 milliamps, which is 400 microamps. The minus just means it's leaving the circuit, leaving the gate up here. Oops, let's take a look at it. Leaving this. Don't forget, that's a source current. It's sourcing to other devices. And for every device you connect, that leakage current was 40 microamps in the high state when this is high. So how many of these will feed? How many of these will tolerate before it gets to 400? Well, this is TTL spec, and you'll be able to calculate that in a minute, but this is the general equation. The high-level fan-out is IOH max. That's the maximum current this will put out, to IH max, the maximum current that this input needs to work right. And if you make that calculation using the specs for different logic families, you can determine how many high loads you can drive. What's the high level fan out? And for TTL, I want you to make that calculation by looking at the specifications, again on page 273. And you'll see that the high level fan out is 10 again. Now, the low level fan out and the high level fan out were both 10. You could drive 10 different circuits here. You could go out to 10, take one output, TTL, and you can go to 10 different circuits. They're guaranteeing that. But the low-level fan-out and the high-level fan-out aren't always equal. Sometimes one's 10 and the other one's 20. Sometimes they're the same, like in TTL. So you'll work homework problems, and hopefully that'll clear things up for you. That concludes this lecture.